structure, electronic structure, and periodicity. Atomic structure, electronic structure, and periodicity. We'll study the basic structure of an atom. The basic structure of an atom. We're going to draw this. The basic structure of an atom. It's okay. Now that let's see. An atom contains protons, neutrons, and electrons. An atom contains protons, neutrons, and electrons. An atom contains protons, neutrons, and electrons. The protons and neutrons are found inside the nucleus. The protons and neutrons are found inside the nucleus, while the electrons exist in energy levels. While the electrons exist in energy levels around the nucleus. Energy levels around the nucleus known as the orbits or shell. So that's it for the basic structure. We're going to number 2, properties of okay, just add it where you are. Add that these particles are called subatomic particles. Don't shake it there. Before we take the properties, number 2, and atom. You people. reaction. So according to this school of thought, an atom will come from any matter. When matter is broken down into smaller particles, it will finally arrive the smallest part that can no longer be divided. We'll call that one an atom. So other people will say an atom is the smallest indivisible particle of matter. According to Dalton's atomic theory, put it down. You people are making noise. It's okay. You people are making noise. According to Dalton's atomic theory, John Dalton proposed John Dalton proposed 5 postulates. Postulates, famous among which are, so the famous of his postulates. John Dalton proposed 5 postulates, famous among which are matter is made up of tiny particles, tiny indivisible particles, put it that way, called atoms. Matter is made up of tiny indivisible particles called atom. Matter is made up of tiny indivisible particles called atoms. Atoms of the same element are identical. That's another point. Atoms of the same element, they are identical. Okay. When atoms combine, they do so in whole number ratios. When atoms combine, they do so in whole number ratios to form compounds. Now, according to John Dalton, his first postulate is that people are still making noise. According to John Dalton, atoms, elements that are made up of, or matter, generally matter is made up of tiny indivisible particles, and we call them matter. We call them atoms. Now, according to him, these atoms can no longer be divided. Don't you push not pass here again, you are disturbing. So, this is chalk. Yes, you will got the outside. If this chalk is broken into small pieces, continually broken, you take that one, you break again, you break until you have the smallest piece, which can no longer be broken again. We will call that one an atom of this substance. 0. Yeah. So, but now, the discovery of subatomic particles. That's where we will go to now. But before we go there, let's now give those properties of that will be number 3. Let me see what will come first. Let's take subatomic particles. Okay. Subatomic particles, join it, and properties. Because subatomic particles will no longer be strange. According to John Dalton, Joseph John Dalton, that is his name. We can no longer divide atom. But however, atom has subatomic particles, which is a disproof of Dalton's atomic theory. The subatomic particles include a number of protons, neutrons, and electrons. Subatomic particles. For each of these subatomic particles, we'll look at 3 things. We'll look at number 1, the mass. We'll look at the charge. We'll also look at its position within an atom. In an atom, where can we find it? So that will constitute the atomic particles, subatomic particles with their properties involved. Okay, protons, they have a mass of 1, a charge of +1, and they are found in the nucleus of an atom. Neutrons, they have a mass of 1, a charge of 0, because they are neutral, 0, and they are found also in the nucleus of an atom. Now, electrons have a mass of 1 on 1,840, meaning they have negligible mass. Negligible. A charge of -1, they are found in the energy levels around the nucleus called shell. saying this. An atom of an element can generally be represented. Let me clean this so that. Let X be the symbol of an element. Then we can write this. If given the symbol of any element, maybe sodium, hydrogen, we can write the element like this, where A, we already said X, we have let X to be the symbol of the element. A is what? Mass number, thank you. And Z, atomic number. Now, an element is made up of atoms of that element. Which means the proton plus the neutron. This means that mass number of an element is equal to the number of protons plus the neutron number. Therefore, we can define mass number. Also, we can find proton number as mass number minus neutron number. This means proton number is A minus N and N is A minus P. Now, what about atomic number Z? So, we'll take this down. We'll define atomic number Z and mass number A. So now, mass number A. This refers to the sum of the number of proton and neutron. Put it like that. Define mass number as the sum of the number of proton and neutron present some of the number of protons and neutrons present in the sample. Atomic numbers can be defined in terms of protons, can also be defined in terms of electrons. So it is the number of protons in the nucleus of an atom. Number of protons in the nucleus, or the number of electrons on the shell of the neutral of the atoms of the neutral elements. Yeah. I think we should be page number 4. Isotopy. Isotopy is the existence of two or more atoms of the same element having the same atomic number but different mass number due to the difference in the number of neutrons. Isotopy is the existence of atoms of the same element having the same atomic number but different mass numbers due to difference in the number of electrons. Sorry, the number of neutron number. Example, chlorine. What's the atomic number of chlorine? 1735. And fluorine, 1737 are isotopes. Hi. Yes. Come again. Carbon
12
and
14.
good. They are also isotopes. Okay, so okay, another example is a carbon 12, carbon 14. The boy wants to be serious. Even hydrogen with an atomic number of one proton. We call it hydrogen. Hydrogen with atomic number 1 and 2 has mass number, meaning that here we have proton plus neutron. We call it deuterium. And hydrogen, 1, 3, 1 proton and 2 neutron. Okay, deuterium, we call this one tritium. Yes, there are also isotopes. In more concept, we already define RAM and relative molecular mass. So we're going to skip that and we'll rather look at the relative isotonic masses. Then we'll look at the mass spectrometry. Okay. Okay. On mass spectrometry, we'll first look at the relative isotopic mass. You already know about the relative atomic mass, mass of one atom of an element compared with 1/2 of the mass of one atom of the isotope. Relative molecular mass, mass of one molecule of a compound compared with 1/2 of the mass of one atom of the carbon-2 isotope. So now, relative isotopic mass, take it as a definition, is the mass of one atom of an isotope compared with 1/2 of the mass of one atom of the carbon-2 isotope.
Isotopic mass.
Yes, relative isotopic mass. Mass of one isotope, one atom of an isotope, compared with 1/2 of the mass of one atom of the carbon-2 isotope.
Compared to 1/2.
1/2 of the mass of one atom of the carbon-2 isotope. Then the next we'll look at the relative formula mass. So the formula here is mass of one atom of an isotope divided by 1/2 mass of one atom of carbon-2. Now, relative formula mass. What are you doing here again? Relative formula mass is the mean mass of one molecule or the mean mass of one formula.
What?
The mean mass of one formula unit molecular unit of a substance compared with 1/10 the mass of 1 atom of the natural acid. The mean mass of one formula unit, the substance compared with 1/12 the mass of 1 atom of the natural acid. Now we're going to look at the mass spectrum
of the mass of one atom.
of the carbon 2 aspect. The mass spectrometer is a method of determining relative atomic and molecular masses. There are 5 processes involved in the mass spectrometer. The first chamber is the vaporization chamber. So I'm not going to draw it here because on the diagram here is very clear. Yeah. So, and to save time, so I'm not going to draw. There are 5 stages involved. One is to vaporize the sample, to turn the sample into a vapor. So we have the vaporization chamber. And the job of the vaporization chamber is for the sample to be vaporized. Then after vaporization is the ionization. After ionization, it is being accelerated to an electric field. Accelerated to an electric field. Then it is being accelerated again to pass through a magnetic field and then deflected. Magnetic field and deflection, and then last is detection. Detected and recorded. Yes. So we have the vaporization chamber first, then we have the electron gun to ionize the sample in the ionization chamber. So after ionization, it is being accelerated to an electric field. Okay, so from the electric field, it passes through the magnetic field, and the magnetic field deflects the ionic sample, yes, to the ion detector. So the last chamber here is known as the ion detector. That is the mechanism of the mass spectrometer. So with information from the mass spectrometer, they can ask you to calculate the relative atomic mass or the relative molecular mass of the compound. I'm going to do one of such. The two sketches show the mass spectra obtained from atoms of two different elements. In each case, determine their relative atomic mass. So there is a formula. I've not put it here in the notes. There's a formula to determine the relative atomic mass. Using this. So I'm going to give it now because it's not in the notes. I don't know why I did not try that one. Anyway, so the relative atomic mass is the sum of relative atomic masses times relative abundance divided by the sum of the relative abundances. So now, we have to determine the relative atomic mass for this one, and then maybe I'll give you this one before and do it come out with the relative atomic mass. So this is the mass to charge ratio that is given here on this axis, and then on the alternate the height. So now we have two isotopes in this case here, in the first case. So the relative atomic mass here is the sum of relative atomic mass times this. Okay, so we're going to take 50.5 times. Now we are being given this in percentage. That one there's nothing given there. Okay, so we'll go with this one. Okay, so I have to come and complete this. Even though it's not here, I'm going to come out. So 50.5 times 79 plus 80. Is it 81 times 49.5. We divide by 100. It is given in percentages, and the whole of the percentage is 100. More so, I think if you add this, you should have 100. Yeah. So this calculation gives you the relative. Let me see. Calculator is absent. Anyway, this gives you the relative atomic mass. And remember, the relative atomic mass has no units because it is a ratio of masses. It's mass over mass. It always has no units. And then you can expect to answer in about 3 significant figure, 1 decimal places. Okay. Then here there's no scale given, so I'm going to complete it and then it will become an assignment. That's of atom structure. Okay. So I'm giving 3.8, 2.4, and 1.2. This is assignment to find the relative particles. Now, that will be the end of the atomic structure. We will look at electronic structure.